So till now we have seen what are vector spaces, what is meant by linear combination of vectors, linear independence of vectors, and spanning set, and so on. However, all these notions are restricted to within a given vector space. So in this video we will see how if there are two different vector spaces, say V and W, how they interact with each other. The tool with which we will be studying this interaction is called as linear transformations. Linear transformation is a function from a given vector space to another which satisfies certain nice properties, which we will see in a moment. Let me start with a definition. So linear transformations are central to the study of linear algebra, in particular this particular course. We will be studying various properties of linear transformations for a long time. Not specific linear transformations, but generally of linear transformations. So let me first define what a linear transformation is. Linear transformation. So let V and W be vector spaces. Now till now W was a vector subspace of V in various cases. That is how these notations were being used. However, that's not the case now. V and W are two different vector spaces. Yeah, as needless to say, I'm always considering vector spaces over R here. A function T, that's called T for transformation, from V to W is called linear transformation if the following are satisfied. So it's a function, in particular it satisfies the following. 1. The addition in V is preserved. In other words, if we take two vectors, look at the sum and look at its image, it will be the sum of the images. So let me write it down, it will become clearer. T of V1 plus V2 is equal to T of V1 plus T of V2. And the second condition states that the scalar multiplication is also preserved. So in other words, T of CV is equal to C times T of V. So this is for all V1 and V2 in capital V, the first case, and this is for all the second case, C, a real number, and V in capital V. So let's spend a couple of minutes trying to see what is happening here. Let's use the green color to denote. So let me circle the vector addition V1 plus V2. So I would like to point out that this is happening in V. This is a vector addition which is happening in V. Now red is being used to circle out vector addition. However, remember that this is a vector addition in W. Even though I am using the same notation, I am not specifying where it is, but the context makes it clear. So it's your job to slowly start identifying where which operation is happening. So as you can see, this red is a vector addition which is happening in W. Why? Because T of V1 and T of V2 are vectors in W. So the vector addition has to be in the vector space W, isn't it? Similarly, this scalar multiplication, that is also happening in V. C times V is a scalar multiplication which is happening in V. At the same time, this scalar addition, this is happening in W because T of V is a vector in W and C times T of V is happening in the vector space W. So that is what it says. It's in some sense preserving the structure of the vector space. The structure in V and the structure of W are in some sense compatible through T. All right. So let's look at some examples of linear transformations. Examples. The first example and the I should say the simplest example will be the map T from a vector space V into another vector space W be given by T of V is equal to, as in 0 of the vector space W. Let me just write it once or twice to point out that this is where all these things are happening. So this is the 0 vector in W. Every element of V is being mapped to the 0 vector. So this is called the 0 transformation, linear. This is called the linear transformation. It's called the, oh yes, why is it 0 linear transformation? We have to check that. That's quite straightforward. Let me just do that for a couple of cases. Okay, so before we proceed, I would like to maybe state a lemma, which I will leave as an exercise. So when is a function from a vector space V to W a linear transformation? It is a linear transformation if both these conditions are satisfied. What we will do through this lemma is to simplify it. We will just put one condition to check for a particular function being a linear transformation. So let T from V to W be a function between vector spaces V and W. Then T is a linear transformation if and only if T of V1 plus C V2 is equal to T of V1 plus C times T of V2 for all V1, V2 in capital V and C a real number. So I'll just leave this as an exercise. It's quite straightforward. You have to show both sides here. If T is a linear transformation, you should show that T of V1 plus C V2 is equal to T of V1 plus C times T of V2 for all V1, V2 in V and C in R. And similarly, the converse would be if T is satisfying this, prove that it is these two conditions are satisfied. These two conditions of a linear transformation. Okay. Well, with this lemma, let us start looking at more examples. Before we go into a second example, observe that in example 1, T of V1 plus C times V2 is equal to the 0 vector W, and this is just the same as T of V1 plus C times T of V2. Why is that the case? This is also the 0 vector in W, this is also the 0 vector in W. A scalar times 0 vector is 0 and the sum of 0 vectors is again the 0 vector. So yes, this is certainly a linear transformation. Let's look at the second example. Let's call this particular map I. So T is not necessarily the only alphabet you should be using. I from V to itself be the function or be the map given by I of V is equal to V for all V in capital V. Again, check that I is a linear transformation. This particular linear transformation I is called the identity linear transformation. Identity. So these are two very important and very straightforward examples that we should immediately look at, and let's now look into slightly more interesting examples. Let's see, T be a map from R to itself, be given by T of let's call it x, an element in R is sent to m times x for a fixed real number m. Then T will be a linear transformation. So just to quickly check that, T of let's say x1 plus cx2 will just be equal to m times x1 plus cx2, which is equal to mx1 plus mcx2, which I will write it as cmx2, which in particular is T of x1 plus c times T of x2. So when there is just one vector or one element x1 on which T is acting, I will slowly stop writing the brackets around it. So T of x1 and Tx1 should be in the same thing. Alright, so this proves that T is a linear transformation. So in other words, dilations or scaling by a fixed number is a linear transformation. Okay, what could be a good example next? Yeah, let us look at T of, so T of, okay, to T be a map from R2 to itself, where T of some vector, let's say x1 comma x2. So T of this is equal to x1 plus x2 comma 2x1 plus 3x2. This is a map from R2 to itself. So one can quickly check. So maybe I should do the check at least in the initial stages. Let's see if x1 x2 plus say c times x1 y1 and x2 y2. So maybe here as well, let me change it to, so it was x plus y, 2x plus 3y. So this is equal to, what would it be equal to? This is equal to T of x1 plus cx2 comma y1 plus cy2, which is equal to x1 plus cx2 plus y1 plus cy2 comma 2 times x1 plus cx2 plus 3 times y1 plus cy2. Let's see what happens when we expand this out. This is equal to, so finally what do we want? We want this to be T of x1 y1 plus c times T of x2 y2. That is what we want. So this is going to be x1 plus y1 comma 2 times x1 plus 3 times y1 plus cx2 plus cy2 comma 2 times cx2 plus 3 times cy2, which is equal to, so this is already equal to T of x1 y1, and in the second case this is going to be c times, just take out the c common here because this is actually multiplication by, okay, I'll just write it down. This is x2 plus y2, 2x2 plus 3y2, which in particular is equal to plus c times t of x2, y2. So, I'll slowly stop doing all these checks for every case, and I'll slowly start giving them as exercises to you. So, this in particular proves that this particular map is a linear transformation. Well, the previous example was from R2 itself, this was from R2 to itself. So, let us now just look at some example where the domain and the range are different. Let T of x1, so T be a map now from R2 to R3, where the map is given by T of x1 comma x2 is equal to x1 plus x2 x2, 3x1 plus 4x2, 9x1 plus 10x2. Check that T is indeed a linear transformation. Yes, at this point, let us focus on how we can rewrite this in order to see if it can be realized as multiplication by a matrix. I am sure you should be familiar with matrix multiplications. So, if vectors in say R2 and R3 can be written down as columns. So, if we write vectors in Rn as columns, Rn in general as columns instead of rows, what can we write this as? This is basically telling us that T of x1, x2, this is the column representation of the vector x1, x2, right? This is equal to x1 plus 2x2, 3x1 plus 4x2, 9x1 plus 10x2. This is the column representation of the image. But what is this? This, if you observe carefully, is 1, 2, 3, 4, 9, 10. This matrix multiplied to the column vector x2, x1, x2. So, what we have done is we have realized that there is a matrix which is corresponding to this particular linear transformation. So, that naturally motivates us to ask the following question, which will be our next example. The next example being, let A be an M cross N matrix with coefficients in R, of course. Then define T of an N vector. So, right now we will be treating all these as columns, right. So, this is x1 up to xn to be equal to 8 times the vector x1 to xn. What will be the solution here, or what will be the result here? This will be an element of Rm in the column representation. So, where this is the matrix multiplication. What we will finally be able to see is that T is then a linear transformation. We will come back to this later, certainly. So, if you can take the effort to painstakingly write down the explicit expression of T of x1 to xn here in terms of the coefficients in A, it is very straightforward to indeed check that T is a linear transformation. So, I will not go into the details there. The point here is to note that right now we are trying to realize matrices as linear transformations. So, as I said, later we will realize that we will see that every linear transformation T can be realized as a matrix. So, we will come to all that later, but it is crucial to make this observation right now that matrix multiplication is indeed a linear transformation. We are only looking at linear transformations in Rn, but maybe the next example will tell you that that's not necessarily restricted to just Rn, obviously not. So, let T be the map, let's call it something else. This actually has a classical notation to it. Let D be the map from P of R to itself, where D of a polynomial is its derivative P prime of x. Then check that from calculus you should know that D is a linear transformation. The reason why I mentioned that you should know this from calculus is because we know that if you look at the derivative of sum of two polynomials, it will be the sum of the derivatives. And similarly, if you look at the derivative of a constant times a polynomial, it is going to be the constant times the derivative of the polynomial. So, yes, it is indeed a linear transformation. So, note that this is not necessarily a map from P of, it is certainly a map from P of R to itself, but we could also think of D restricted to say P5 of R or P4 of R. Observe that D from say P4 of R, if you take a degree 4 polynomial and look at its derivative, you will end up with a degree 3 polynomial. So, this is a polynomial in P3 of R is also a linear transformation. I would at this point make the distinction that the example which I am underlining in green is technically different from the example which I have underlined in red, because the vector spaces from which the linear transformation underlined in green is P of R, and its range is also P of R. That is not the case in the case where it is underlined in red. It is a map from linear transformation from P4 of R to P3 of R. So, even though the map is the same, I did not write the map, but the map is exactly the same. What is the map? The map is basically where D of P of x is the same thing, the derivative. But it is important to observe that the moment we talk about a linear transformation, there is a domain and there is a range, and they are important, even though it is technically the same derivative that we are looking at. So, I will just note this as a different, okay, let me not confuse too much. I made my point with words, so that is enough here. Okay, another example might be to look at the example of the vector space R infinity. Let me recall that this is the vector space x1, x2 dot dot dot, the infinite sequences where xi's are all elements in R, and T from R infinity to itself be defined by T of say x1, x2 dot dot dot. This is mapped to by shifting it to the right. Okay, why are there two brackets not needed? Right. So, check that T is a linear transformation. T is called the right shift operator. It shifts the vector to the right. So, it is called T is called the right shift operator. Okay, so we have seen quite a lot of examples now, and we will be seeing many more examples in the next few days. And let's right now stop with examples and start studying the properties of linear transformation. All right, so the first lemma, it's a simple result. The first lemma which we would like to prove here would be that every linear transformation necessarily maps the zero vector to zero vector. So, let T from V to W. So, before I just go ahead, observe that, go through the examples which were listed again and observe that we are not restricting our definitions and examples to finite dimensional vector spaces. As noted, P of R to P of R is a linear transformation. That is an infinite dimension. It's not a finite dimensional vector space. Same is the case with the last example which was given, which was from R infinity to R infinity, which is not, which actually is an exercise to you to show that R infinity is not a finite dimensional vector space, and that this is an example of a linear transformation from an infinite dimensional vector space to itself. Alright, so this lemma T from V to W, this lemma states that every vector space, every linear transformation from a vector space V to W should necessarily map 0 to the 0 vector of W, 0 of V to the 0 vector of W. Then T of the 0, so after this lemma, I will slowly stop writing the subscripts V and W, which will be clear from the context, but let me write the subscripts in the proof of at least this lemma. So, let us give a quick proof of this statement. So, what do we have? This is the same trick which we have been using for proving these kind of results. We are interested in T of 0 of V, and this is nothing but T of 0V plus 0V. But T is a linear transformation. So, this is equal to T of 0V plus T of 0V. Now, let us add the additive. Remember that T of 0V is some vector in W. Adding the additive inverse of this vector T of 0V to both sides, what do we have? We have 0 of W, because the left hand side has only a T of 0V. If you add it to the additive inverse of T of 0V in W, we get the additive identity of W, which is the 0W. That is equal to, yes, I will leave it for you to check that this is 0W plus T of 0V, which is equal to T of 0V, and that completes the proof.